So up to this point, we've been talking mostly about electricity, electric charges moving around and doing all the things that we need them to do in the modern world. At this point, we're going to start talking about magnetism. Now, if you remember back to the very first part of the class, we said that there's really no difference between electricity and magnetism. You can't separate the two. They are actually two forms of the same thing, and we'll investigate that and why that's true towards the end of this section. But just like we separated out the electric effects from the magnetism, now we're going to do the opposite. We're going to separate some of these magnetic effects from the electric charges or the electric fields that we have dealt with up to this point. We can't do it completely because what you're going to learn is that a changing electric field produces a magnetic field. So you can't brain dump everything that you've learned up to this point. You're going to need it. But we'll try to focus on the magnetic part of the story so that then you can put the two together and see how they work. All right, let's get started. Okay, so take a look in your books under the magnetic fields section. Before we can really talk about magnetic fields, let's kind of have to define what they are. And it all comes from the fundamental difference between an electric field and a magnetic field and what produces them. So we knew that let me get my pen here. We knew that if I have two parallel conducting plates, and I connected them to a battery, I could separate out the charges, just like that. And that's going to generate my electric field. So having a single charge here, we could also do the same thing. And the field lines kind of look like this. So this is called an electric monopole. And mono, of course, just means one. And so this, because it's positive, it's got a single pole. I could also swap it. I could make it negative, and it would still be a single pole. Now, when we put two of these, let me erase some of my field lines here. Let's say that we took a positive and a negative charge. Do you remember what that would look like? What does the field lines look like there? Remind yourself, because using Faraday's laws are actually very important. So the electric field went from positive to negative. And so if I had anything over here, then it would land like this. And so it would land like this. And then maybe I had some coming out this way. Maybe I had some coming out this way. Something like that. So this device, when I have two of these charges, when I have two of these poles, then we said that was an electric dipole. Di means two. So we've done all of this. This is all, nice and normal, and you should be pretty familiar with it from now. What's different, if I take a magnet, let's say I take a bar magnet that looks like this, and maybe we'll have a north pole here and a south pole here. And let's suppose I want to separate out the north pole from the south pole. So I'm just going to cut it right down the middle. When I do this, and maybe you've experienced this for yourself, when I do this, I actually get two new bar magnets that looks something like that. So it's impossible for me to get just a north pole of a magnet without having a south pole. There's no way to do that. And what this means is that magnetic monopoles don't exist in nature. There doesn't seem to be any way to create a magnetic monopole. The only type of magnetic field that exists is a dipole. And so that's going to have some important implications for this. But all that means then is, no matter how many times I break this, I'm still going to end up with my north and my south magnetic poles. Okay, so since there is no such thing as a magnetic monopole, there's also no concept of a magnetic charge. You can't really talk about a magnetic charge. That doesn't make any sense because we can't have just a north or a south. So instead, the way we rate the strength of a magnet is through something called the magnetic dipole moment. Now, don't get confused. Moment has nothing to do with time. It's not some short instance of time or anything like that. To a physicist, a moment means something that's applied at a distance that's going to make it rotate. Most common kind of moment is a torque. And in fact, in engineering, usually you don't use the word torque. You use the word moment. It's when people say moment, they actually do mean literally the torque. Another example you may have run into would be the moment of inertia, which talks about how the mass is distributed, but it also is telling how that object is going to rotate. So our magnetic dipole moment is doing the same thing. And the way you can think about it is this. Let's suppose, let me just redraw this magnet just to give myself a little bit of space here. So let's suppose I have a magnet that looks like this, and we'll say that this is the north end, and we'll say that this is the south end. And let's suppose that I have another magnet at some angle here that's free to rotate. And we'll call this south and we'll call this north. What's going to happen to the magnet? This rotating magnet, what's going to happen to it? Well, it's going to rotate counterclockwise so that the south pole of the rotating magnet is lined up with the north pole of the stationary magnet. Simple as that. Now, if I had no magnet here, then if I had no fixed magnet, well, then the rotating magnet is just going to stay still. So the stronger the magnets that I have, the more torque is going to be applied, the faster it's going to move, the greater the force it can apply. So talking about this rotation of the magnet gives us a way to measure the strength. And so that's what we mean when we're talking about a dipole moment. We're talking about how strong the magnet needs to be, or how strong the magnet is, by measuring how fast it's going to rotate from that. All right, so take a look down at microtask 1 in your book. And it says the magnetic moment's direction is always through the center of the dipole, going from south to north. So in this case, if I were going to draw the magnetic dipole here, the dipole moment, then it's going to look like that. So it's got a distinct direction. How about this one, the rotating magnet? What direction is its magnetic dipole moment? Now it's going to be just like this. So you see that I can have an orientation of that arrow, that magnetic dipole moment can change around. And by the way, we need some symbols. We always need symbols for any quantity that we're talking about. The probably most common used symbol is this lowercase Greek letter mu for the dipole moment. You will also see that. I find that confusing, even though it's pretty common in engineering. I find it confusing because it looks like a vector mass, which doesn't really make any sense when it comes down to it. So we're going to be using this Greek letter mu to represent our dipole moment, our magnetic dipole moment. It's also just called a magnetic moment. And then, but just be aware, you'll probably see that M with a vector sign over it before. All right, so in microtask 1 then, what kind of quantity then is the magnetic moment? Well, we've got an arrow over it, so you probably figured out it's a vector. But the key thing here is that it has a direction. So it has a strength, it has a magnitude. That's what's determining how strong this magnet is. But it also has a direction. If I have my, let's say this is north and this is like this, so that my magnetic monopoles, my magnetic moment are lined up, I'm not going to get any torque at all. And so it's not going to rotate. So the direction of it matters a great deal. So therefore it is in fact a vector. It's got a magnitude, it's got a direction. So let's take a look at microtask 2 here. We're just going to slide this over. So you've probably played with compass needle, and you know that for a compass, a magnetic compass, it's going to have generally a red end and a white end or a silver end, things like that. The red end is usually what we call the north end of the compass. It's the one that points to the letter N on the compass. And if you do experiments with this, it's kind of interesting. If you take a magnet, a bar magnet or whatever, that north pole, that north magnet, the red magnet, will always point to the south end of any nearby magnet. So, given that description, what is the polarity, and by that I mean north or south, of the magnetic field at the Earth's geographic North Pole? Think about what that means. Geographic North Pole is, the top of the Earth here. So if that red magnet on the compass is pointing towards that geographic North Pole, what must be the polarity of Earth's magnetic field at the North Pole? It's actually south. And so our magnetic field is currently upside down. So at the north magnetic at the north geographic pole, we actually have our south magnetic pole. And the poles actually flip every 50 to 100,000 years. It varies quite a bit. We can actually see that. So currently, in fact, our magnetic north pole our magnetic south pole is not even on the geographic north pole. It's drifted a little bit, and that happens. And so this is why, if you're a pilot or something like that, you have to correct for the magnetic heading. If you go to the true heading, well, you're not going to land on the runway, and that's kind of embarrassing. So that, oops, switch to my pen. There we go. So then we know that that must be the south. Okay, now imagine that each one of these little squares that you see here in the picture, in the diagram here, is a magnetic compass with the little needle. What I want you to do is pause the video and draw the direction that needle is going to point. Where is that red arrow going to be pointing? Really important that you see this. So pause the video, do a quick sketch, and then let's talk about it. Hopefully you pause the video because this can get a little confusing sometimes. All right, so remember that we said that that needle in the compass is going to point towards the South Pole, right? Well, that means it's going to be repelled from the north, and so it's going to look something like that. And obviously down on this side, it's going to be pointing towards it. Should make sense. Now, when I get up here, let's go to number 5 up here. When I'm at number 5, then it's going to point this way because it's going to try to bend back over and point at the South Pole. At 3, it's going to point this way. Again, it's trying to point towards that south. And then 6 is going to be here. So you should be able to kind of visualize what that is. Now, the bottom side is going to be just the opposite. So here, it's going to try to bend towards that South Pole. It's only going to point away when it's directly lined up with that North Pole. Then here it's going to go this way, and then this way. So now what we want you to do, now that you've drawn those, is we want you to connect those lines. So it would look something like this. Now notice that I've skipped block 9. What direction would that compass point if I could put it inside the magnet? I can't, obviously, but if I could put it inside the magnet, which direction would it point? Use this line, this loop that we've just drawn. What direction do you think it would go? Well, sure, it's going to continue and it's going to go this way. So if I am inside the magnet, it's going to point from south to north. So that right there is the magnetic moment. It's showing us the direction of the magnetic moment. Now, the same thing occurs if I go this way and get another loop that comes back in, and it looks like this. So what this is the magnetic field. You've just drawn the magnetic field lines. We traditionally use the symbol B with a vector sign to represent the magnetic field. Why not M? Because we use M for a lot of other things. So our electric field then would look like this, whereas our magnetic field, we're going to use a B for it. So notice that just like the electric field, that magnetic field has a direction and a magnitude. Let's switch colors here. If I'm standing at this point right here, then maybe my magnetic field is kind of in this direction. But if I'm standing here, it's this way. And that shouldn't surprise you much. The same thing happened with the electric field with that as well. So if we have a direction and we have a magnitude, what type of quantity must the magnetic field be? Well, of course, it's going to be a vector. Anytime I have that direction, that's kind of your clue that it's going to be a vector. All right, now look down here at the bottom. Let's switch back to hand. There we go. So the magnetic potential energy then is defined to be the magnetic moment multiplied by the magnetic field. And so the magnetic moment is how strong that magnetic field is. And then the magnetic field vector is telling us our orientation to the magnet. Because, if I had my south and my north pointed at each other, well, there's no potential energy stored there because it's not going to move. On the other hand, if I've got a north and a north, well, okay, they're repelling each other. And so I can get that rotation coming with that. So both of these vectors, let's go back to black. Both of these quantities are vectors. The magnetic moment and the magnetic field are vectors. So we're going to have to use one of the two methods we have for vector multiplication. So let's flip over to the next page here. Switch to here. Okay, so look at microtest 3. So based on your choices, what type of quantity is the magnetic potential energy? Don't be fooled. It's energy. All energy is a scalar. So don't lose sight of the things that we've been talking about since the very first semester. So I've got two vectors, and I want to get a scalar out of it. Will I use the dot product or will I use the cross product? Well, this is why we often refer to the dot product as the scalar product, because it's going to give me a scalar by the time I'm done. Now, what I want you to do is think about this. We know that it is going to involve, our expression is going to involve this, and that's going to be for the magnetic potential energy, which we'll use maybe a UM for that. So pause the video, and I want you to write down an expression for the magnetic potential energy based on what we've talked about. You got it? Okay, well, it's just going to be our UM, that's an M, promise, equals mu, and it's going to be dotted into V. Simple as that. So remember that that dot product involves an angle, and so if my relative angle is going to tell me how much of that magnetic moment and the magnetic field is actually contributing to storing energy with that. So the picture that you have here, this is an actual permanent magnet, and what we've done is we've dribbled iron filings around it. Now, iron itself is not a magnet, but it responds to a magnet, so it will turn as a result. Not all materials do, and the example we give here is copper, plastic, a couple other things don't. But the class of materials, and it's a very large class of materials called magnetic materials, will act like a magnet when there is a permanent magnet nearby. And so you can see that each one of these lines that you see here, it's like if I'm drawing here, let's do a different color. Each one of those lines, that's the result of these iron filings, then draws out my magnetic field. So you get something that looks very similar to our magnetic field lines for an electric dipole, but now it's a magnetic dipole. And again, the big difference is I can't cut this in half. If I cut it in half, I'm just going to get the same picture from that. All right, so take a look at microtest 4 then. So the loops that we drove through the compass needle were two of the loops. Maybe we might consider, maybe it was this one and maybe it was this one. And of course, remember, it goes all the way through the magnet on both sides. So looking at this picture, where are the field lines closest together? I'll go ahead and delete those that were there. Where are the field lines closest together? Close to the poles or far from the poles? Well, you can see when I get into this region here, they're very close together. They're all actually going to be bunched up into one little thing. So given that, and think about the analogy with Faraday's rules, where is the magnetic field going to be the strongest? Again, close to the poles. And you can think of that two ways. One, we know from Faraday's rules that if the electric field lines are closer together, we've got a stronger electric field. But you also know that if I take two magnets and I put them closer together, the force that I feel, that attraction or repulsion, is going to be stronger the closer that I get. So both of these kind of make sense. So yes, they're both going to be closer to the poles. Now, this next part that we have down here, we're talking about flux. Now, we defined an electric flux to be the number of field lines that penetrated some surface. So, maybe our simplest case we had looked like this. And so that gave us our electric flux. So the problem that we have here, and I'm just going to delete this page. If I can find my hand, here we go. The problem that we have here, though, is we think about it. I can't have just lines moving away. I always have to have these closed loops because I have to have a dipole. I can't have a monopole or anything that looks like this. So my magnetic field lines are always going to be closed loops. So let's take that same surface. Maybe I'll take a plane. I can use any kind of Gaussian type surface that I want. And if I have field lines that come here, remember they're going to have to be a closed loop, whatever that shape of that loop might be. Hopefully you can see that. So the number of field lines entering that surface must equal the number of field lines going out. There's no way to, if I don't, then I don't have a closed loop. Think about that and see if that makes sense. If I don't have the same number going in as I do coming out, I must not have a closed loop. I must have something that's free and going off by itself. So what is the total magnetic flux through any closed surface? So, even if I were to draw, a sphere or something like that, and then my magnetic field lines penetrated that, I'm going to get the same result. Well, 0. So because I have the same number coming in as I do going out, then the total must be 0. So if we're going to, we talked about Gauss's law, and we said that only the perpendicular component contributed to the flux. Well, the same is also true for the magnetic flux. So what I want you to do now is pause the video, and I want you to come up with an expression for the magnetic flux. And remember that our electric flux, the definition of our electric flux, looked like this. So this was our electric flux. Can you come up with a definition then, an expression for the magnetic flux? Pause the video, stop and think about that, see if you can do it. Okay, so the the magnetic flux then, at any given point, at any particular point, must be B dotted with the area. So the number of field lines going through there, going through that area, whatever that area is, that's going to equal my magnetic flux. And so that should make sense to you, because now I've got that dot product. So only the field lines that are perpendicular to the surface are going to count for us. And we've done this before with electric fields, and the same thing applies with magnetic fields. So Gauss's law for electric fields uses this definition of electric flux. And this is not Gauss's law, remember. Gauss's law is that the flux is equal to the charge enclosed divided by epsilon naught. So don't get confused. This is actually the definition of the flux that we used in Gauss's law. So what we did was we found the flux going through one tiny part of that surface, and then we integrated over the whole surface. So what I want you to do now is write down Gauss's law for magnetism. Don't think too hard about this. It actually is it's as simple as you think it is. Pause the video if you need to, write that in there. So the definition of my Gauss's law form for my magnetic flux, then I'm going to have to integrate over that entire surface, but now instead of the electric field, I'm going to dot that area vector, that dA, into my magnetic field. Now, what is that integral equal to? Go back to the very first part of this. We said that all the field lines that go in to a surface also have to exit that surface. Every one of them. There has to be a match pair for every one of them. So what is the total magnetic flux for any closed surface? Well, it's 0. And so the equivalent of Gauss's law for magnetic fields then would be to say that the integral of B dot dA must equal 0. So even though the electric and the magnetic fields are very similar, they are not identical. And if you think about it, there can't be any concept of an enclosed charge for a magnetic field. So the fact that this is 0 then kind of makes sense with that. And while this may be difficult to come up with some calculations for finding the magnetic field, for example, we're going to use this when we start looking at changing magnetic fields and how those magnetic fields can generate an electric field. So this Gauss's law for magnetic fields is actually quite important. So today we introduced the concept of the magnetic field, and we talked about how it's kind of related to the electric field, but not exactly the same. It's going to be real important that you think about and always keep in your mind, where is it similar to an electric field and where is it different? That's going to make it a lot easier for you to understand the concepts that we're talking about with this. So you don't want to just have to start from scratch and say, oh, magnetism is completely different. I'm going to forget everything that I learned. No, a lot of what you've learned with the electric field is going to apply to that magnetic field with some tweaks. So for the rest of this section, and we're going to start introducing those tweaks slowly so that you can see what effect a magnetic field has on all the things that we experience in our daily lives. All right, we'll see you next time.